this working? Thanks, James, for that introduction. Yeah, so my name is Justin Riley. I'm the team lead for software infrastructure at the Research Computing Department, Faculty of Arts and Sciences at Harvard University. Today I'm going to talk about basically how we reinvented the system that James just sort of sneak previewed that we had when I got here about 2 years ago. And so this is an overview of sort of the path that we took to replace that old system with a better one with OpenNebula and stuff. I guess I better stay up here. Whoops. So just to start off, we'll talk a little bit about virtual machines at FastRC. So basically what happens is, right, we as you saw, we have a lot of bare metal compute. We maintain a massive Slurm cluster along with a lot of fast scratch storage and a ton of lab space storage as well. But in addition to all of that, users also have sort of special needs that don't really fit that mold, obviously. So we'll get tickets from users. They're wanting to set up some special service that doesn't quite fit in with the bulk of our infrastructure. We kind of look at the request, we figure out the best route. Sometimes it's, yeah, let's spin you up a VM. Sometimes it's another solution. But if that happens to be the best option, we basically get this VM up and running for them, make sure all the critical services are running all the time. And it's important to note that these type of services are generally things that are not ephemeral VMs. These are not VMs that come and go. These are more or less the same as physical hardware with respect to their expectations for uptimes. Some examples of this, right? So the typical thing of I need a website, right? So we do research group websites. Sometimes we want a development environment from converting our code that we're developing from the development environment to production. There's a whole plethora of web-based visualization tools, different types of API servers, web-based workflow engines such as Galaxy. We have private GitLab servers, various web and non-web front ends to various systems, including a fish tank, believe it or not. We do all kinds of things. And then obviously we use VMs internally to power a lot of services on demand. And so as James kind of alluded to, we had an old system that we were looking to replace. So when I got there, or when I came to FastRC, we had basically a big KVM cluster, unfortunately backed by a 2-node cluster storage system, which is not exactly ideal, to say the least. It all resided in a single data center. We had manual VM scheduling. Every time we wanted to launch a new VM, it was like we were bootstrapping a bare metal server using Pixie boot. Manual VM resizing, so if we decided, oh, this thing needs a little more RAM, more CPU, we have to kind of verse power it down, verse edit the script, fiddle the numbers in XML and start it back up. Of course, we had some custom helper scripts, Perl scripts, or dodgy Perl as we like to call it, for some of the core tasks like building VMs and getting hypervisor stats and doing manual, hey, this hypervisor looks like it has a little space, let's pop it there. So all of this was sort of unfortunate. And really, in addition, as I'll talk about in a little bit, we had some instability as well with the system, which was really the main driving force for reinventing it. So in the new setup, we obviously landed on OpenNebula. Still on top of KVM, we replaced cluster with Ceph. We decided to use we split the new system over 2 data centers, technically 3, but the bulk of it in 2. This provided us automated VM scheduling. We have image-based OS deployments now, so VMs coming up are super fast. Dynamic VM resizing via OpenNebula, and then we also implemented a pretty belt and suspenders multi-tiered backup system, as you'll see in a bit. So why OpenNebula and Ceph? Well, as James just showed, that slide came basically from John and I early days playing with OpenStack. OpenStack wasn't a complete dive bomb for us. It was just an incredible sink of time. So we were able to have some success with it, but just getting the configuration and figuring out what the single best distribution and version of that code and all the numerous services that it has was kind of a daunting task. We actually ended up landing on something called Kala, which is containerized OpenStack, which actually was early days, but really promising. And it actually had kind of every component of OpenStack nicely containerized and documented. So that we really liked that model. But at the end of the day, the configuration was still pretty heavy, even with that simplification with Docker containers. So obviously, right, OpenNebula, primarily for us, it was light and simple. As you saw, we spun up VirtualBox. I had it working in a VM pretty much the same day I played with it. And it's very flexible. As you'll see, we were able to integrate it very easily into our environment. So just sort of a throw out, so we, just a shameless plug, I should say, for containerized OpenNebula, a project called Corona. This is inspired from the Kala project from OpenStack. We still liked the idea of being able to run all of OpenNebula inside of a container so that when new releases come out, 5.4, something goes bump, we have a backup of the database. We have the old container that we used, exactly the software stack that we had. We could roll back. So that's really the big thing we're looking for out of this project. It does exist. It does work in some capacity. We're looking to overcome some obstacles. If you're interested, feel free to ask us about it after this talk, and feel free to look at the code and contribute. So why Ceph? Mainly it has pretty wide adoption. It's an open source Red Hat project, right? Distributed file block and object store. Has Rados at the core. User accessible S3. There's no single point of failure, self-healing, exabyte scale. We saw a lot of success out of CERN using this, and so we said, why not? Anything's got to be better than a 2-node storage cluster. And so Ceph was sort of our natural choice there. So just moving on to the architecture, what we ended up doing is, so we have actually 3 data centers. We have one at Harvard, which is shortly sort of going away, but nevertheless, we have another data center at One Summer Street in Boston, and then we have a third data center, this data center C, which is actually MGHPCC, the Holyoke data center that James described. And so basically we have controllers, hypervisors, Cephmons, and OSDs running in both data centers in Harvard and Boston. The controllers are active-passive with an active-active MariaDB cluster, although that's about to change to Galera, and then we'll probably also make some additional changes with the new release. But basically, so some of our networks span both of these data centers. So for those networks, we're able to live migrate VMs across data center A and B. The Cephmon out in data center C is really just to maintain quorum for Ceph in case any of the data centers go down. We always have at least 3, ideally. The nice thing about this setup is that, and with OpenNebula too, is that we can live migrate VMs to machines so that we can do maintenance. That was one of the big pain points in the old system, that if we needed to actually repair something on a server, it was actually kind of difficult to do because we didn't have the automated way of saying, oh, just drain this node, clear it all off so I can shut it down, do some work on it. So that's been a really big benefit of that. And obviously, in addition to that, we have the public cloud add-ons that we've enabled currently just for Azure, but we imagine we might do some more of this in the future. It just depends. Maybe not. Load testing. So, right, we came up with this architecture. We said, great, this is cool, but in the early days of KVM, really one of our big problems that motivated us to want to replace the whole thing in the first place was VMs you'd have a rogue VM or two that goes crazy on storage and then starts to spin the rest of the VMs out, and eventually getting into read-only state, which became an administrative nightmare. So to make sure that we had actually designed something that wasn't still susceptible to that, we used OneFlow to deploy a Salt, Diamond, Grafana, Graphite stack. So Salt is basically just so we can do remote orchestration, like execute commands remotely on a bunch of VMs. Diamond to collect a bunch of stats about them while they're running, and then Grafana to kind of make plots, and we can make it arbitrary plots based on any of the data coming in. And so what we did was, okay, let's spin up a ton of VMs. We'll run Bonnie++, we'll run HPL Unpack, get a bunch of CPU and I/O intensive workloads going. We tested live migrating while those workloads were going between data centers. While they were running, we would pull OSDs, kill mons, watch Ceph, how it reacted, the rebalancing, And then we did some fine-tuning of Ceph parameters based on those experiences. We monitored file access and system uptime via SSH on each of the VMs while this was happening, so we could see what it looked like inside the guest OS. And then obviously, based on all of this, we also made some minor-based VM image tuning where we got rid of swap altogether on our base images and did things like increase the SCSI timeout so it was a little more resilient too if Ceph was rebalancing. So that was the architecture. We put that in place. We've been in production for a little while. That unfortunately wasn't the only bit that we had to do. We also had a number of other integration points. We need to be able to deploy this really easily. So at FastRC, we use Puppet to manage everything, pretty much. And so we needed to be able to deploy OpenNebula with Puppet. And so to that end, we found ePostDev's Puppet module on the web. We forked and provided several patches up to them, including the support for the latest 5.2 version, and we'll continue to do so for 5.4. It's been great. We can automatically provision multiple OpenNebula clusters, which we already have. So we have a cloud a test environment to where we can just kind of bang around on OpenNebula and not worry about affecting production things. We have our production VM infrastructure, and then we have a third cloud that I'll talk about later that's coming. That's massive. And we also use this Puppet module to launch OpenNebula inside of OpenNebula. So whenever things like 5.4 beta come out, we actually spin up a complete OpenNebula and Ceph stack inside of OpenNebula just using VMs. Obviously, we're not looking for performance there. We're looking for things that are going to break in terms of our workflows and needs between releases so that we don't have to go through the troubles. Just real quickly, the backup system. So our production Ceph cluster, we do daily VM disk snapshots. We do 2 weeks worth of those. We take the delta between today and yesterday. We transfer it to a backup Ceph cluster out of Paranoia. And we apply that to a sister block object. So basically, the very first copy is expensive. Every day is generally a much smaller amount of data you're transferring to backup. And then to be even more paranoid, more belts and suspenders, we dump those RBDs on the backup system to QCOW2s and sync them nightly. There's a utility that John wrote to do this, to go from Ceph to our snapshot to rotate the backups with QCOW2. If you're interested, the link's here. This will get out of the way. And the real reason to have this backup cluster is for that when we do these QCOW2 conversions, it just keeps load off the production cluster, again, out of Paranoia. A little bit about monitoring. We use an open source Ceph dashboard, and then we also ship all of our sort of low-level Ceph stats to Grafana so that we can make kind of plots to use while we're in any case where we need to deep dive when we're having issues with Ceph. So far, so good though. We've also integrated some Ceph Nagios alerting so that we know if anything goes sideways with the storage. This was a big one. So we also created VM leaderboard. So OpenNebula 5.4, I believe, has a little bit of this, or it gives you these sorts of stats on a per VM basis. What's really nice about this, and John will actually point this out in his lightning talk, so if you want to know a lot more about this, you can get all the gory details from him later. But the nice thing is that when these VMs would go read-only, or we would have issues with the infrastructure, it was always hard to kind of figure out who's creating the issues. So not just having per VM IO sets, but being able to overlay them all and say, okay, out of all of you, who's the leader, right? So this graph is always updating. The hypervisor is basically, there's some code that we wrote to collect stats from Ceph at the hypervisor level to tell us, what are the stats for each of these guys, ship them to Grafana, and then we make custom plots. So we can see those sorts of things. We had to develop at least one OpenNebula hook. Unfortunately, we have some shared networks between VMs and physical, so we don't live in a perfect world. We have VLANs that have some VMs, some that have bare metal, and we really don't want them clobbering each other. So just to be extra cautious, because people can just point and click very easily in Sunstone or with the command line tools, right? So what happens is we do a reverse DNS check on the VM name and make sure that the IP that it matches DNS if it has the same name, so that they don't clobber anything that exists on the existing infrastructure. If it happens to be a mismatch, then you get an error message that we update the VM instance attributes so that on Sunstone you can see why your VM was suspended. So this hook, when it detects this case, will actually suspend the VM. And this runs on the create and running events. And then if you resolve the problem by essentially renaming the VM and getting the IP differently, it basically, whenever you resume, it'll tell you this was fixed and allow the VM to load. We developed one DNS. This is very, very similar to the hook that dynamically updates DNS in the example that we did in the workshop yesterday. But this can sort of run anywhere. It handles multiple NICs. It does the same sort of name sanitation. And it runs outside of the OpenNebula hook system. All it does is just query on an interval. We might add an API to where a hook could just kind of ping it and say, hey, I've got a new node. So if nothing else, it's a simpler hook to write. But it's deployable via Python pip or Docker. It's built using DNSLib and Python OCA, which is really nice Python binding. It's a little dated by now, but it still works with even most recent OpenNebula. OpenNebula images, we're actually using Kanaya, which is a spin-off project from one of the OpenNebula team members, Javier Fontaine. It's on GitHub. It's basically, I describe it as Docker file for containers, sort of, right? There's no fine-grained image layer caching like Docker has, but it is a simple YAML file format. It exports to QCal2, uses libguestfs and QEMU image under the hood so that you're not actually doing a full OS boot, which means that you don't create a lot of cruft in your images. You can kind of create clean, pristine images. So it's been really nice. Allows us to kind of keep a single Git repo to have all of our base images. You can have images that derive off of each other. On the left here, right, we have an OpenNebula enabled CentOS 7.2 that's extremely minimal. On the right, the right one builds off the left one, and this is our customized FastRC based CentOS 7 with some utilities that we like to see by default. VM bootstrapping. So we saw yesterday in the workshop, right, you can specify startup scripts, which is really great, except that we often need to change these scripts. We don't really want to do that through OpenNebula. We generally like to do that through Git. So we sort of wrote one startup script file to rule them all, which we called OneVM Bootstrap. It's up there on GitHub now if you wanted to play with it. It probably needs some work to be really versatile across multiple OSs, but it works pretty well for now. But it essentially just clones the Git repo based off context variables. So you specify a repo in a context variable. You specify a branch if you want one. Otherwise, you use the default. Then you specify a path in that repo to run. And then when we execute the script, we take all the context variables and make them available to the script as environments. So the script doesn't need to go and mount the CD-ROM and source context.shell. That's all done for it. And then this also logs the standard out and standard error, or logs standard out and standard error to a file, sorry, as well as the total runtime for the startup script. And this allows us to just push changes as necessary, and we don't really have to touch the templates. They're just set. Use cases, really, the last item is probably crucial here, right? Anything a script can do is the use case for this. But today, we use contest scripts for all kinds of things, provisioning hosts using Puppet, Chef, Ansible. You can, right, that's how we would automatically tie a node into our Puppet infrastructure. We use it to launch OpenNebula and Ceph, as I described before, inside of OpenNebula for testing. Really cool use is spinning up dynamic GitLab continuous integration runners. So these are things that run on push. So whenever you push to a repo, you can say, oh, go run this continuous integration task and report back. So we can just dynamically spin up workers as needed, take them down, they auto-register, auto-deregister. And then RPM builders, and again, anything a script can do here. Obviously, we want to use OneFlow more than we really have all to date. So far, like I said, we've used it for the load testing. It was super crucial for that. And then the OpenNebula and OpenNebula testing has also been useful. But we're looking to do more with this and actually spin up more kind of science-like work, cluster, like maybe a Jupyter Hub cluster or Hadoop or a number of other types of services. So that's sort of an overview of our OpenNebula systems, how we've integrated it, the challenges that we faced. Last slide I'll leave you with is where we're going next. So that was reinventing the old thing, which is great. The old thing was really VMs that live around 24/7. They're here to stay. We need to basically consider them, full-time machines. what we want to do is have some room to allow users to do more ephemeral-like workloads. It doesn't have to only be ephemeral, but we really want to support that where we haven't in the past. So coming up soon, I believe the fall, we're going through a compute hardware refresh, which means all of the Odyssey compute that we had, that James showed in those pictures, that you see some of here, is actually going to go under a hardware refresh, which means we're getting new hardware to replace it. The old hardware, which is still nothing to scoff at, right? 64 cores, 256 megs of RAM, will be converted into a user-facing OpenNebula. So one of the maybe details I didn't get to is that whenever we launch a VM, we're doing everything for them. They have no idea OpenNebula is back there. This is going to be putting OpenNebula firmly in their hands, so they'll actually have access to Sunstone, the command line tools. They'll have some quota, some storage quota for compute and storage. So essentially, we're going to be an infrastructure as a service for FastRC users, and this will be sort of the private cloud 2.0 moving forward. This will all have to take place out at MGHPCC. There's really nowhere else we can do it. We also plan to extend our current production clusters out into Holyoke and federate them, so Holyoke will become a zone to 1 Summer Street as well moving forward. So just some acknowledgements. John Noss is here, Wes Stillingham. John worked on a ton on the OpenNebula side, did a lot of great work. Wes was our Ceph expert, did a lot of great work with Ceph. So thank you to both of you guys for all the work that you've done. Obviously, thanks for Ignacio for visiting with us and really helping us think through some problems and escalate issues with the team. And I know we've bombarded you guys with a ton of issues over time. And special thanks to Javier Fontaine and the entire OpenNebula development team. It's been great. If you want to know a little bit more, James pointed to this as well. We recently had a paper published in the Computer Society, in IEEE Computer Society, so you can go check that out if you like. And thank you very much.
Thank you very much, Justin. Keep us posted about the customer-facing OpenNebula. Yeah, thank you. So we have now a half an hour coffee break, so we'll be back at 11:45.